Welcome everyone to another OCP Tap call. This is call number 148. It's my pleasure to introduce Tadayuki Nomura, senior professional of timing devices at Murata Manufacturing. Tadayuki has spent over 25 years in the field of timing devices, working as both an application engineer and product engineer after earning his master's degree in electrical engineering. Throughout his career at Murata, he has contributed to development of high-performance crystal resonators and oscillators technologies that underpin modern communication systems. Today, his focus is on market creation of timing devices with the goal of enabling next-generation connectivity and networking. His work brings deep device level expertise with system level requirements, making him uniquely positioned to discuss how advanced resonator technology translates into real world performance gains. Please join me in introducing Tadayuki Nomura.
Okay. Yeah. Hello, everyone. And thank you very much, Matt, for your nice introduction with me. So I'm Tadayuki Nomura. I work in Murata Manufacturing in Japan. So let me introduce my topics here. So the title is Best in Class Phase Noise for Next Generation Connectivity by Super High Frequency Crystal Resonators. So let me start from the background and motivation. So as we know, the ICT that's importance is getting increasing. There's no doubt. Of course, one of the reason is to obtain a generative AI services, and also so we are using the network daily, right? And then that's going to our lifeline in our modern life, and then so especially in Japan, so I'm expecting it so we can keep using that technology even in disasters. So we have our desire to that technology going forward to match to make our life better more. Then in a case one of the in this situation one of the challenges now the coexistence of performance improvement and power saving is desired in the market. Then to solve that challenge, so I developed the gigahertz level crystal resonator for basic class phase noise to realize next generation ICT. That's the background and motivation. Then, so when we when we think about the performance of a connectivity and also the clocking point of view, so we need to touch on the PLL phase lock loop. Then the upper left picture shows the very simple general structure of a PLL. Then PLL has been developed to generate a high frequency clock with better phase noise as local oscillator for the communication. So that's why we need to touch on this point. Then, in simple, the PLL phase noise is given in combination of phase noise by VCO in PLL circuit and also the reference clock in a PLL. And the bottom left picture shows the general structure of a phase noise of PLL. The gray line shows our VCO phase noise. Yeah, always the poor phase noise, even that can generate high frequency. Compared with that, the oscillator or resonator can achieve much better phase noise, but the frequency is kind of low. So then by using a PLL, so we can obtain a high frequency and a kind of a better phase noise as shown in red here. Then our task is how we can improve this phase noise. Then so there are three ways to improve phase noise. The first one, the bandwidth expansion of a PLL itself. And the second one, improve in-band phase noise. And the last one is improving the VCO phase noise. So I'd like to take a look one by one. And first, the bandwidth expansion in PLL. So as you can see in the top left picture, so we can improve the phase noise if we can expand the the bandwidth of a PLL itself. So in a case, we need to bring the cutoff frequency more higher, as shown in the picture. But cutoff frequency of PLL is reciprocal of time constant of a PLL operation. So that's why, so that expansion should be limited, as shown in bottom left. If we bring the cutoff frequency more higher without any other changes, so it is possible the 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 we can obtain desired frequency and stability more faster. But uh, if we bring the cutoff frequency too high, in that case, no convergence happen, and then that's a kind of very common issue in a PLL. So we need to take care, or let's say we need to take a balance of performance of phase nodes of PLL and a PLL operation. And then also, when we take a look the transfer function of PLL, so let's frequency multiplication by PLL rather than PLL bandwidth. So we can say high frequency difference gives expansion of a PLL bandwidth with a room of a stable PLL operation. The second one is in-band phase noise improvement. Then top left picture shows again the structure of a phase noise of a LO through the PLL. And then the PLL in-band phase noise is given by phase noise of reference clock and frequency multiple ratio by PLL. So low phase noise reference clock with higher frequency. So that means less multiplication by PLL gives phase noise improvement at PLL in-band, as shown in the bottom left. So low phase noise with high frequency reference clock gives phase noise improvement, we can say. And last one, the VCO phase noise improvement. So this covers outband of a PLL. Then, but in general, so many different type of PLL design is going forward, and then still that's a topic of a research in academia and possibly in industry. And in general, HC circuit on CMOS is used for the VCO because the making the L and C on the semiconductor is kind of easy by using other technologies. And also that technology is very useful to making a higher frequency. Then when we're considering how we can improve the phase noise of VCO, so we need to improve the Q of L and C on the semiconductor in VCO. In a case, one of the challenge might be a high frequency inductor on CMOS because so in general way, so to improving a Q of an inductor, so we need to have more turns, and also another approach is changing the material, the core material as inductors. But the more turns that takes some more space, that brings a more high cost as a semiconductor. And also the change in the material itself is kind of uh, quite challenge in semiconductor to bring the magnetic core or something like that. So in the case, so improving the phase noise of reference clock with its expansion seems economical compared with improving uh, the VCO performance on the semiconductor itself. So the first conclusion here is, so we took a look the way to improve the phase noise on the PLL, and high frequency and high Q reference clock is an economical way to improve the phase noise, PLL phase noise. So our next question is, how high frequency and Q reference clock is possible? Then, when we are considering high frequency crystal oscillator, there are two ways to get a high frequency and a high Q. The one is using a PLL. It's kind of easy. In combination with usual crystal resonator like a megahertz range with PLL, we can make higher frequency. But as we learned previously, so that brings our worse phase noise. So it's not a good choice. So the one of the other way is bringing a high frequency crystal instead of like using a PLL. So that seems the good way compared with using a PLL. But if it is possible. Then again, so next question is how high frequency crystal is feasible? And then also we need to understand what is the challenge to achieve such high frequency crystal. Then let me touch on a little bit detail regarding the crystal resonator. So in the market, mostly so 80 cut quartz crystal is used in the market and then right now. And then in a case, so the thinner thickness of a crystal element gives the frequency. So in a case, so if we can make more thinner crystal element, so we can obtain a much more higher frequency. It's kind of simple. And then that uh, equation is gives like bottom left. And then the N stand for the N is resonant order. And then usually to avoid any risk of abnormal or unwanted frequency oscillation, so using a fundamental response is preferred in the market. So that's why, so N should be 1. So in that case, so as you can see, the thickness gives a frequency, and a thinner thickness brings a more higher frequency. Then in this case, that we aimed the 983.04 megahertz. That is our 8 times higher of 122.88 megahertz, which is usually used in base station RF previously. Then our the target thickness of a crystal element is going to the 1.7 micrometer. So compared with the 48 megahertz, so you can see much more thinner, like 20 times. So the challenge is gonna be the handling of the crystal element itself and also the thickness control in production. That's going to be the key to achieve such high frequency crystal resonator. Then by using our let's say the production machinery which is already available in the Murata, so we could have workable resonator samples with such high frequency in the 3 by 3 millimeter ceramic package. The package is at this moment, so the purpose is the feasibility study. So that's why, so we just use the 3 by 3 millimeter ceramic package. Kind of, it's very easy to get from the market. So then, so you can see the representative parameters of this high frequency crystal that we can see in the table left. Then, in general, so Q by F is constant when we take a look at crystal resonators performances. Then in this case, with let's say around the gigahertz fundamental frequency resonator, so we achieved 7.5 trillion as a number of Q by F. Now, compared with usual 48 megahertz 80 got crystal in the market, so I can say so the Murata can achieve 3 times higher Q with high frequency. So I can say so performance expected resonator has been achieved here. And then we need to have an oscillator circuit because the crystal resonator is a passive component, and then we need to have a oscillation circuit. So in collaboration study with Professor Razavi in UCLA, So we could arrange a simple CMOS oscillation circuit. That design is optimized to our resonator and then designed on the TSMC 28 nanometer. And then we aim the simple design to achieve low phase noise and low noise and power. And then you can see the circuit diagram and also the picture of our piece evaluation board in the left. And the test it has been placed in same package with the resonator, and then they supplied 1.2 volt for both CMOS oscillation circuit and circuit core and output buffer. Then this is a measurement result of a phase noise. The top left shows the measurement result phase noise, and then again, representative measured key value are shown in the table left, bottom left. And then simply say, so this measurement could achieve 3.59 femsec RMS jitter from a 12 kHz to 20 MHz offset frequency range at 983.04 MHz. And the noise floor of a phase noise reached out almost minus 180 dBc per hertz at 10 MHz. And power consumption as the oscillation core is 1.32 milliwatt. And then the figure of merit as oscillator is going to the minus 287 dB. Including the output buffer, the figure of merit is going to the minus 270, almost 279 dB is achieved. Then this is a comparison with existing technology in the market. So I picked up some other technologies from other vendors, which are saying the better phase noise or high frequency. In the case, as you can see, so I could achieve best-in-class phase noise with low power ever in the market. And then on the table, bottom left, so I can say, so I could mark the best figure of merit as an oscillator in the market. This is the final page. So conclusion and the future work. So again, we realized the best-in-class phase noise cross crystal oscillator at almost 1 gigahertz. And then using this oscillator as reference of a PLL, stereo clock performance can be expected that has a potential to realize next generation communication. So that's why I like to implementing this technology to the market with the partners. So for implementation, because the frequency changing is kind of not easy work. So that's why system level technology development is required when we are trying to using this technology. So that's why me and Murata is looking forward to have an opportunity to of the collaborative technology development to realize next generation communication with researchers and engineers who is developing the future ICT. Yeah, thank you very much for your attention.
Great. Let's open the floor for questions.
Yes, please.
How we can follow up on your research collaboration with Professor Razafi,
Okay.
because he's very famous in this area.
Uh-huh.
So he's one of the
Yeah.
very well respected people in this area. So I personally I would like to follow up on the research collaboration between Murata and what he is doing in his lab in UCLA.
Sure. Okay. Let me explain a little bit the cooperation with Professor Razavi. give me a sec. I need to have a water. So, yeah. So I also know that he's very famous and then kind of legend in the CMOS RF design. Then, so I contacted him to try to making a more fundamental technology improvement going forward. And then, so we could have an agreement to working as a collaborative study on that. But so the topics here is based on the collaborative study with him. Then, but because of our smart smart context point of view, as you can see, the circuit itself is quite simple. That means so it is designed to optimize the advanced our gigahertz crystal resonator, but the CMOS circuit design point of view, there's no invention, just optimization that is commented by Professor Razavi. So that's why he didn't publish on these topics as himself. So instead of that, so that's why I I issued this paper in a European microwave conference that was happening last end of September, and then I touch on his name on the paper. So to follow up these topics, so I think it is better to check my paper first, and also it is also good to contact to the Professor Razarbi on these topics. He's also keep working to very fundamental and more advanced technology to achieve a better communication technology in the semiconductor. I'm not sure this is
No,
uh I
that is good. That is good.
okay.
Yeah, that is good. But how I can access your paper?
Okay. Uh do you have access right to the IEEE's the research in the paper website? I'm not sure the name though. So now that my paper is available in a site, and then
Yeah.
so
Can you put
and
can
also
you put can you put a
you can
link
find
to
you
it in the chat?
so you can find my contact here, email. So please contact me.
I
So
suggest you share screen, just go on IEEE Explore, show it, because this stays
mm,
on the record and then people can see it. I think it's good.
Yeah. So Ahmed,
Can you repeat, Hasham?
do you have a link to the conference or the paper? A link
No,
where I can
not on
access
top
the
of
paper.
my mind. Takayuki, can you put something right now up so people can see it?
Exactly. If you can just put a link
Yeah.
to the
a link.
proceedings or the paper,
Okay.
and
Okay.
I will get it
Wait a minute.
from IEEE Explore or something.
Sure. Wait a minute. Uh, I'm now trying to get the link. Okay. Wait a minute. Uh. Okay. Wait a minute. えっと I just put the link in a chat.
Fantastic.
Hmm.
Yeah,
Yeah,
that's
very
all I
appreciate it.
need.
Take a look.
That is all I need. Thank you very much.
Okay. Okay. Yeah. Hope you can enjoy
Mm.
my paper.
Thank you. It is really a great presentation. Seriously.
Hmm. Okay. Yeah. Thank you very much for your nice comment.
I have a question.
Oh, yes, please.
I think I see like Tatsuya. Tatsuya, you go ahead first.
Oh, all right. Thank you very much. I'm not a specialist here. I'm a beginner here, so I don't know and so much. But you have not discussed about the phasing about the noise when detect the phase in the PLL. We will not discuss the noise when we suffer when the system detects the phase difference in the high frequency. So such a detection noise is, I assume that according to your talk, and I've never heard that such kind of noise detecting the phase difference. That is completely negligible in that case, and just the phase noise of the reference and the source oscillator. Those two are the main, and so the detection noise is totally negligible, and that's why we don't need to discuss. Is this right? Or if the multiplication factor goes slower, and then some point we have to think about that how much how low noise we can detect the phase difference in the for the PLL. What do you think about this?
I'm not sure I could catch enough your question, but how I can say it, regarding the PLL itself, I think now still I'm sharing the PowerPoint slide, I guess. Then so
Yeah.
are the to detect detection of the phase differences. So probably we have two topics. One that happen in the PLL itself, and the other one is RF itself. And PLL is developed for the purpose to have high frequency and enough phase noise in comparison between a VCO clock and then reference clock.
Yes.
Then in a phase frequency comparator or detector, so that portion always comparing the phase differences. But with this loop circuit, so this circuit is trying to align the phase itself. That's the purpose of this circuit. So in the end, so phase difference is going zero when we could have a desired frequency and performance. So and then in an RF, so itself, that is a kind of the challenge. So we, I'm actually, I also I'm not so expert of RF itself, but the frequency, no, phase differences is the key to establish the modulation itself, right? So in modern high-speed communication, so OFDM technology is always used, like Wi-Fi or cellular communication. So that's usually utilizing the differences of amplitude and also the phase between RF signal and also the, let's say, on local oscillator clock. So, so in the case, the difference is kind of matter to establish the RF communication itself. Then the point is, yeah, always we need to achieve the RF communication or even wired communication. So the phase detection is a key. So then we are going more advanced technology, and then modulation is getting more complicated. In a case, more, let's say, stable and pure phase noise local oscillator would be needed. Otherwise, we cannot recognize the difference of a phase in a signal, RF signals. So
Okay. Yes. Yeah. Just my point is here. We have the PFC. PFC here if this PFC has the noise of the intrinsic noise, then I think the PLL is the noise will be output in the of the VCO, and so then, but I think probably here what I thought is yes, black line VCO phase noise and red line phase noise that is in the high frequency. It's slightly red one is higher. I wonder that part, slight part. Slight difference could be due to the detection noise at the PFC. But anyway, yes, I noticed that here this shows that yes, probably the difference, the noise in the PFC is quite small. Yeah, thank you very much. Yeah.
Yeah, thank you for your question. And then just in case, so why I put this red line a little bit higher than that's a showing purpose. So ideally it's same. It should be same.
All right, thank you very much.
So you mentioned that you wanted to collaborate with
Yes.
with us to help advance your research in this area. So what do you expect from the OCP tab group to do?
Yeah, right, good question.
We need to help, but how we can help?
Yes. Yeah, at this point. So in my understanding, so the more top priority on the crystal resonator itself is how the crystal resonator can achieve high frequency, high Q to realize the best-in-class phase noise in the market. But in this page, so you can imagine if the thickness is going more thinner, but in actual production, so if the accuracy of the actual production is same, in a case, frequency variation through the production is getting wider. So somehow I need to have frequency tuning function enough for the application. Like for example, usual megahertz crystal resonator oscillator, let's say the resonator has a plus or minus 20 ppm frequency accuracy in overall, not only just at the room temperature, but also over temperature or something like that. Because of that performance, the most of the communication technology has been established on that. So, but if now I'm going to the 20 times higher frequency, like a 1 gigahertz from 50 megahertz, in a case, so it is possible the frequency variation is getting wider 20 times. Actually, not going to the 20 times. Now we are in development of a technology, but still it seems like achieving a more better frequency accuracy by this gigahertz resonator itself is quite challenging. So that's why I like to see the technology which can bring the frequency tuning function from a CMOS oscillation circuit or PLL. That's gonna be my the topics I'm looking for in collaboration.
I have one sort of detailed question. So can you go back to
Yes, please.
the slide for with the RMS jitter comparison?
RMS jitter comparison. Here?
Next one. Yeah, this one. Yeah. So the RMS, well, first of all, how do this RMS jitter being calculated? Is it like integrate over the phase noise down to a certain frequency, or
Yes, right. So in simple, the
you
phase
just
noise and RMS jitter is kind of quite same, but the 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 RMS jitter is standing on time and
okay, yeah. So then
phase
my
noise is
question,
standing on Then
Is
integration. Yes.
oh, so here my question was actually how at down to which frequency do you integrate? And it's 12K hertz is the lowest frequency you take integrate. So I mean, when you compare, do they all integrate down to the same frequency? Or I mean,
yes, right. So I'm not sure 100% the history of crystal oscillators, but always the crystal oscillators were kind of similar technology. The RM's jitter performance is based on the 12 kilohertz up to 20 megahertz, kind of standardized. I'm not sure why.
Yeah, that's
Probably
my
standing on the
question.
previous
Okay, good
technologies.
to know. And I'm more interested in the lower frequency performance, but they are not usually discussed. I mean, so they are usually discussed in terms of more like alarm deviation and so on.
Yes.
Yeah. Okay. Okay, I understand. But do you happen to have the alarm deviation of your oscillator?
Not yet. Because again, so this technology development is very focused on the high speed communication in future. So there always the matter of the range, the offset frequency range is kind of 12 kilohertz up to 20 megahertz, or a little bit wider though. But at that time, so alarm deviation or such low offset frequency range is out of scope. So that's why we are not measuring it yet. But
Okay.
so I understand your point. Yes.
Yeah. So I mean, if that is measured, then collaboration is inside of the scope now. So I just want to mention that to you.
Yeah. So
But
still,
until then,
so yeah. And so in my understanding, so this topic is also the standing on the clocking, right? And then in my understanding, clocking fundamental technology contribution is there are two contributions. One is to achieving a high frequency, high speed communication, and other one is of course time synchronization. And then because of our subject offset frequency range is different, so the covering both is ideal, but still it's quite challenging from a technical point of view, I guess, to achieving an ultimate goal in same time with one clocking technology, or
yeah,
let's
so
say the crystal
I'm trying
oscillators.
to touch what Hesham was mentioning. How can we collaborate? And I
Yeah.
see the gap there. So if you could try to bridge the gap, then I think it would really help to sort of for the
Yeah,
collaboration.
right. Yeah, very appreciated. Yes. So right. I also have kind of same sense because so even I'm talking about the high frequency crystal resonator for the communication, but the communication infrastructure itself is established in combination of such RF technology and also the time sync technologies, right?
That's right. That's
And
right.
especially
Definitely.
on the design, my customer design, they have both in the same PCB or same hardwares. So always we can consider how we can collaborate from that point of view.
Yeah. Okay. Thank you.
Yeah. Yeah. Very appreciative for your question.
So quick question, Tadayuki.
Yes, please.
So,
Yes.
and Nobu is also here. Like, in terms of, let's say, if you want to synchronize two of these oscillators, is there like an advantage when you can go like to a higher frequency, or like, I mean, as far as I understand, because it's a natural frequency, you're locked. You cannot do much in terms of like, let's say, steering or trimming, right? Or is there like some temperature that you can apply to do some trimming? You get what I mean? Nobu, like, can you take it from here? Like, basically, can this be used to, let's say, do something like wireless interferometry? Throwing it at you guys.
No, I mean, so what Ahmad is asking is sort of touching the sort of similar topic. How can we utilize both the communication side and the timing side to the simple application, like ranging is one of the application that both comes in together, the sort of high frequency side and the synchronization side. And
Yeah, right. Yeah, right. I'm still working on that topics and then not enough yet, but so again, so from my perspective, I need to have some technology to tune the frequency of this technology to desired range. But in same time, so in the market, so like a MIMO or distributed
that's
MIMO,
right.
so
Mm.
which are requesting a more accurate synchronization with high-speed communication. So probably, so we can find some collaboration, technology development, or like a, let's say feasibility study or something of the technology to realize that technology more achieving a better performance in the areas. Then yeah.
Yeah, so when you start to do anything have to do with distributed anything, distributed MIMO, distributed or passive or distributed
Mm,
radar or any of those. Yeah, you need to synchronize or at least syntonize the oscillators to sort
yeah.
of do any significant or meaningful phase measurement.
Mm, yeah.
How
Then
about this? Let's say you take the communication off, just have the oscillator sitting. You try to make them to line as much as possible. Is there something like this you have?
I guess for that, first step would be to take the Alan variance of two oscillators.
I see.
It's my take, but I don't
But I
know
mean,
what you
I'm
think.
I'm trying to see what are your knobs to do some trimming or tuning, or there is none. Because you're
Oh,
taking the PLL off, the PLL was basically where we were able to hedge some changes, but here we don't have that anymore. So is there something else that's introduced? Like can we change the temperature, I know in general, I think it's necessary when you take the PLL off, it was gonna give you some trimming because in the loop you were able to modify the voltage, but now
yeah.
that's gone.
Okay. Let me touch on that things. So why I'm trying to avoid in a PLL here is because we're to make in case we are trying to make in a higher frequency by fractional LPLL, that brings a worse phase noise. That's the point. But compared with that, even I'm not measured yet, but the PLL only for the frequency tuning purpose, that might be not that's not bringing a big impact regarding the phase noise.
Yeah,
So in that
but you have
case, so we get a PLL.
some unwanted physical effects. Let's say, for example, again,
Mm-hmm.
temperature. Can that be now
Yeah.
used to steer, your oscillator within something? I mean, perhaps
Mm-hmm.
it's still sensitive to temperature. Nothing changes. It's like a
Oh yeah,
natural
yeah.
frequency.
Uh-huh. Yeah, right. So in the case, yeah. So in actual product, when I'm considering, so I need to, of course, need to take care of our temperature compensation too, like adding the temperature sensor inside of our ASICs of oscillator, and also the the somehow the frequency tuning function with memory, how much frequency tuning we need to apply in that temperature or something like that. It's kind of usual way for the TCX or temperature compensated crystal oscillator. But yeah, that's one of the technology I need to consider.
Is this? I mean, probably I should have asked this first. This is in production, right? You can get this. Is it available or it's not yet?
Not yet. So this
Okay.
so this is not in a mass production yet.
Okay,
So
okay.
technology developed it though. Yes.
So if this is getting produced, is it possible to have a oven version of it as well? I don't think it's a problem if there's a use case, there's a market for it. You just two resistors, you put it in some insulation.
Yeah, I can say possible. It is possible, but from a business development point of view, so first target is the kind of high speed communication, like not only just base station, like a 6G RF, and also like cutting edge optical communication in the data center.
Yeah.
So yeah, I should
Maybe
aim
Noble can work
first
with you
on that
guys. I mean,
direction.
yeah, Noble maybe can directly work with you guys on some sample and let's see what we can do with it.
Yeah, sample is of course available. So
Perfect. All right.
yeah, please keep it. Let me keep in touch.
Wonderful.
And correct me if I am wrong, but your oscillator enhancements can help the accuracy of time synchronization, right? Maybe I'm wrong. Maybe
Maybe I should let Tadayuki speak.
Oh, how are you? How are you, Nobu?
Well, thank you.
I am happy to see you in
Thank
person.
you. So, I mean, this is Japanese friendly time, so thanks
Yeah,
for arranging for Japanese
yeah.
people.
Glad to see you, Nobu.
Thank you. So, I mean, my take is this high frequency oscillator, their performance is optimized for short time sort of performance. And
Yeah.
for the clock, you need to sort of have the phase coherence over a long time. And that part isn't intention, or that part hasn't been explored yet. So that's what
Ah,
Tadayuki has been sort of telling me, that it's still, they are not there yet to make it for the clock use.
got it. Thank you.
Mhm.
I need to be educated. That's all.
Thank you, Nobu-san.
Mm.
Great. Any more questions? I think everyone
Good
had
meeting.
something. Yeah. Go ahead.
Good meeting, Ahmed. I like it. This is very good meeting and very good presentation, really.
Yes. We definitely should
Yeah.
put more often, like Japan friendly time.
Yes.
That's what he said.
Yeah. Sorry for East Coast guys though.
Yes. All the Europeans are sleeping, so
Yeah.
all right. If no
Okay.
more questions, we can probably adjourn.
Yeah, Nobu, are you in Japan now?
Yeah, I'm in Tokyo.
Oh, I love Tokyo. Very good city.
Please let us know when you come.
Absolutely. Oh, thank you, Nobu. All the best.
All
Thank
right.
you.
So again,
Okay.
thank you very much, Tadayuki, for your informative presentation. And we'll see everyone in 2 weeks. Yes, 2 weeks, last day of the year, by a presentation from Paul. All right. Bye,
Okay.
everyone.
Bye.
Okay.
Bye.
Thank you very well. Bye. Keep in touch. Bye.
Bye bye.